So first of all, please feel free to ask any questions in between the lecture. You can ask on chat as well as speak up. So let's start. Okay, so is the screen visible?
Yes. Yes.
Okay, great. So uh, before starting the lecture, let me talk briefly about uh, some motivation for this lecture. Okay, so we define define a conic to be, let's say, roots of a quadratic equation in xy. For example, this would be a circle, and something like this would be a hyperbola. And in general, any degree 2 equation in x and y plus, yeah, the roots of this would be called conics. So consider the following question. The question being, wait, yeah. So why do conics look symmetric? Sort of like, so why don't conics look something like this? And why do they look like this? Or let's say this. In particular, what I'm asking is, why do, let's say, conics have line symmetry or point symmetry? For example, let's say, ignore the case of a parabola right now. Why does there exist for every 2-degree equation? Why does there exist a point P belongs to R square, so that if a particular point, let's say, yeah, P, so that if Q is in the conic, then the reflection of Q in the point P is also in the conic. And similarly for line symmetry, like, why does there exist a line such that if an upper point is in the conic, then the reflection about that line is also in the conic? So this will be like the main motivation for the spectral theorem. And before
Can I make a
state,
guess?
yeah, sure.
Is it because like you can write a conic as like x minus t square plus y minus k square plus some constant equal to 0, and then it just becomes symmetric because these are square terms?
Yeah, great guess. But how can
It's
you
not very
prove that?
formal. Yeah,
Yeah,
like
how
it
can
looks
you
intuitive.
systematically prove that you can write such a thing?
Yeah.
Okay, shift करके we can easily remove the x and y terms, the linear terms.
Okay, great.
And
Yeah.
उसके बाद एक्स वाई वाला टर्म भी रोटेशन के थ्रू रिमूव कर सकते हैं मेरे ख्याल से, तो फिर बन जाना चाहिए.
Okay, so suppose you have a conic like this. Okay, let's take a simpler example and forget about scaling at all. Suppose you have this. Yeah, okay. How do you systematically prove that there exists a line such that if, so we know that, like, believe me that this will be an ellipse of this form, And but without knowing that, how can we systematically prove that the roots would be symmetric about some line? Like in this case, point symmetry is sort of obvious because if
It's by
x, y,
origin, right?
yeah, this is the origin. So how can you prove that there exists some line such that if this is a root of this conic, then the reflection of this about this line is also a root of this conic?
We can try to find some line, like take the equation of line, let's say ax plus by plus c equal to 0, and take reflection of a point xy in that
Yeah,
line. Xy satisfies this x square plus y square plus x equal to 1. Let's say you get
yeah,
the point x dash y dash, and then you also set x dash and y dash uh, satisfying this equation of the conic. So you get two equations, and you have variables two only, like x and y. So uh, no, the variables are, I think, a, b, and c, right? So you need one more equation so that you can find the line of symmetry, I guess. You can do something of that sort, right?
yeah. So indeed, in this case, we don't even need C here because we already know from intuition that the line will pass through 0.
Yeah.
But so I'll be talking about a more systematic approach, like which works in general elegantly.
Yeah, that makes sense.
Okay. So before going through this, we'll have to cover some basic linear algebra. So I'll be assuming that you guys are familiar with like the concept. Like we'll be okay. We'll be working with the vector space Rn in this whole lecture over the field R, and yeah, and the elements of this will denote by this, as the elements of Rn would be column vectors as opposed to row vectors, which is just a convention, but it will be useful. Yeah, and we'll denote it by underlining to emphasize that this is a vector. And we'll use capital letters for matrices. Throughout this lecture, matrices would mean n cross n real matrices. Yeah, and we'll also use letters for bases, and bases would be a set of vectors. Yeah.
This x vector, x1, x2, so on, xn, like here, x1, x2, and xn are also n-dimensional vectors, right?
No,
These are
they are
numbers.
real numbers. So
Oh, okay, yeah, fine.
the vector space Rn has elements, is basically, yeah, consists of these elements where x1 dot 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 xn are reals. So whenever I'll be referring to vector, I'll always write an underline to differentiate between vectors and real numbers. Okay. So first, let's do some change of basis, which would be necessary to state the spectral theorem, which we would use to prove the thing about conics. So, okay. So suppose you have a vector space V, and for the sake of examples, let's consider the vector space R square. So this has an origin, yeah. And what we mean by coordinatizing this space is we just choose a basis. So picking a basis of R square, let's say, coordinatizes it in the natural way, as in for every vector V in R square, by the definition of V1, V2 being a basis, there exists unique alpha 1, alpha 2, so that V is alpha 1 V1 plus alpha 2 V2. And this vector will be called the coordinate vector for V. So the basic idea is that if we have a vector space and we want to convert its elements to sort of column vectors, then just coordinatizing by choosing a basis, we can, this is essentially this as a coordinate vector. So, so let's define the following. Yeah. So, given a vector space V and a basis B, we'll, in this case, I'll use B for the basis, capital B. And then we say that if a vector is written as a linear combination of the basis vectors, then these are the coordinates of V with respect to the basis B. And in this case, this will be ordered basis because the order would matter. Because if we change the order, the coordinates would switch, and we don't want that. Yeah. And this vector would be called the coordinate vector for V. So, for example, in this picture, after coordinatizing R square using V1 and V2 as vectors, we have W, a vector which is, let's say, V1 plus 2V2. And as a coordinate vector with respect to this basis, W is this 1, 2. Okay. Now the question is, can we easily change between two coordinatizations? And what I mean is that if we have R square again, and let's say we have two different bases, I'll take one basis to be the standard basis. This is called the standard basis because of, yeah, 1, 0 and 0, 1. And take any other basis using a different color, I guess. Yeah. Take any other basis. Then is there a nice way to convert between coordinates of this vector in this basis and this basis? So this vector has, let's say, V is this, and this would be written as V is alpha 1 V1 plus alpha 2 V2, and this could also be written as beta 1 1 0 plus beta 2 0 1. So by change of basis, I mean, can we convert between these coordinate vectors alpha 1 alpha 2 and beta 1 beta 2, which are coordinate vectors of V
We can
with respect,
multiply a matrix and
yeah,
we should be able to multiply some matrix to convert it.
yeah, that is what we are getting into. So what we do is we define something called a change of basis matrix, which is a matrix in terms of two bases, B1 and B2. So let B1 be this basis. B1 is a set of vectors which form a basis of an n-dimensional space, and B2 is another set of n vectors. Then look at the coordinates of the second basis vectors with respect to the first. So this thing, like V1 as a linear combination of U1, U2, dot, 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 and so on till Vn. And we just collect this array of numbers to form a matrix. You will see why in a moment. And let's call this change of basis matrix. So why we do this is because of the following. If a vector V has coordinate vectors x and capital X with respect to these two bases, then we have X is this matrix times capital X. So,
Oh, can you show capital P once more?
okay, yeah, sure.
Okay, fine.
Okay. So, the proof of this is pretty straightforward, just some manipulation. So, let's take a vector X in the space, which is Rn in this case, and consider the coordinate vector of X with respect to it. Okay. Okay. So consider a vector X in Rn and consider the coordinate vector of X with respect to the first basis B1, which is a collection of n vectors. So what I mean is this: x1 u1 plus plus xn un, and then notice that this is equal to x, and x is also equal to, let's say, in terms of v's as some other thing, capital X1 v1. Capital X1 are coordinates of, okay, wait, let me make this clear. This is the vector x, and no, I'll not use x, I'll use v. Okay, this is the vector v, and as coordinate vectors, these are the coordinates, like these are the coordinates of v with respect to this basis, and v also has coordinates with respect to a second b2 basis, v1 v2 dot dot dot, and let these be denoted by capital X's. Now we have small vi's in terms of vn using the change of basis, because notice that we defined the change of basis matrix using these coordinates of vi's. So we have x1, and v1 was alpha 11 u1 plus, and so on until alpha n1 u1 un plus, and xn times 1n u1 plus nn un. And we simplify this by clubbing the vectors u1 together, ui's together. So u1 gets multiplied by x1 alpha 11 plus x2 alpha 12 plus xn alpha 1n, and so on. Un gets multiplied by this also, n1 plus x2 alpha n2, and similarly for each I. And this is exactly, so because u1 u2 dot 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 un is a basis, and we have this thing here, that this linear combination is this linear combination, so the coefficient must be the same, because u1 dot 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 is a basis, which gives us this, which is exactly the relation this. So in short, the change of basis matrix is helpful. This matrix is helpful for converting between different coordinatizations of the same space. Okay. And now this is also useful for linear transformations. So recall that a linear transformation is a map from a vector space V to V. Throughout this lecture, think of V as Rn. We'll not use any other vector space. And this satisfies linearity, like these two properties. And now we ask the
What's T called?
T is called a linear transformation.
Oh, okay. T of lambda v equal to lambda times TV follows by the first thing only, right? Why stated specifically?
Uh,
Oh,
no,
that's for naturals. Yeah, that comes for naturals. Okay.
yeah, that's for naturals. Also for rationals, but anyways, yeah, it doesn't follow for reals by the first thing.
Yeah.
Okay, so now we ask the same question. Given a basis B of the vector space V, what does T do to the coordinatizations? Like if we choose a basis, then we essentially coordinatize V. So it turns out then T is just multiplication by a matrix. So let's define this first and then we'll check it. So we say the matrix of a linear transform T with respect to a basis B is defined as this array of numbers where these aij's satisfy these. That for each I, vi gets sent to the coordinate vector a1i, this a1i, a2i dot dot ani. More precisely this. You'll see in a moment why we define this thing. So equivalently, we define the matrix of a linear transform as this. Yeah, this thing. So when I write this, I mean exactly this. Like this is the numbers as a coordinatization using the basis v1. So the nice thing about the matrix of a linear transformation is this. And okay, so this states the following, that essentially what this says is if we coordinatize our vector space V, wait, let's add an page. Okay, so what this says is that if we have a vector space V and we'll be working in R square, and I'll also illustrate this theorem for R square, and the proof for Rn is exactly the same and left as an exercise. So what this theorem says is that given a linear transform T from R square to R square, if we coordinatize the vector space by picking a basis v1, v2, and then look at what T does to the vectors, as in if then the following is true. If T sends V to TV and V is the coordinate vector x, which means that V is x1 v1 plus x2 v2, then TV is given by the coordinate vector mx, which means that if mx is y1 y2, then TV is y1 v1 plus y2 v2. So essentially what this says is that the matrix that we defined weirdly, like just is actually what the linear transform is after you coordinatize the space. So
What is mx here?
yeah, so M is a 2 cross 2 matrix, and X is this vector, like any vector. So let me illustrate what I mean, and you'll see in a minute. So let's say we have R square, and we have a basis V1, V2, and let's say we have a linear transform T, then, and T sends V1 to, let's say, 2V1. Let's do the general case. Let's say a alpha 1 V1 plus alpha 2 V2, and T sends V2 to beta 1 V1 plus beta 2 V2. Then notice that T sends x1 V1 plus x2 V2 to, because of linearity, this, which is in turn equal to this, plus x2. And now clubbing V1, V2 terms, this is V1 times alpha 1 x1 plus beta 1 x2 plus V2 times alpha 2 x1 plus beta 2 x2. And which means that if we coordinatize the space, then the coordinate vector x1, x2 gets sent to this thing. And what this is just this. And this is what we defined our change of, this is what we defined our matrix of a linear transform to be, because this has as its first column the coordinate vector of where linear transform sends v1, its coordinate vector, and b1, b2 is this thing, this.
What are x1, x2? Like any two random vectors in the plane?
Yeah, any two random numbers. Like this is, yeah. So
Okay, so what does this map mean? Like x1, x2 goes to this alpha 1, x1 plus. What's this map basically?
this means that, oh, I mean that T is T is a given linear transform.
Yeah.
And we are given a basis. Then what I mean by this is that the vector x1 v1 plus x2 v2, which I just write loosely as a coordinate vector. This, what I mean by this is that T of this is just alpha 1 wait, x1 plus beta 1 x2 v1 plus alpha 2 x1 plus beta 2 x2 v2. As in, I write this, I'm writing these as vectors because these are like coordinate vectors of this vector, which is a vector in R square.
But the coordinate vectors are still v1 and v2 only, no?
No, wait. V is a vector in R square, and we are coordinatizing the space, which leads to V being essentially, okay. Where is the figure? Okay, yeah. Look at this. So here W could be, let's say, some 3 root 2, any vector. But with respect to this basis, because W is V1, 1 times v1 plus 2 times v2, we say that w, the coordinate vector of w with respect to v1, v2 is 1, 2. So
Yeah.
here x1, x2 refer to those. So right now, just keep this phrase in mind that you don't need to worry about the details right now. Okay, so this is what will be useful, that if we coordinatize our space by choosing, if we coordinatize our space, let's say R square, by choosing a basis, then any linear transform T from R square to R square, our space, essentially becomes left multiplication by the matrix of T, which we defined above, like, yeah. And this sends the coordinate vectors. For example, if in this case, if T would send W to, let's say, it send W to V1 plus V2. Let's add here. Let's say this is T of W, which is V1 plus V2, let's say. Then what our matrix would do, M, what it would do is that it would send the coordinate vector 1, 2 to 1, 1. So is this clear?
Yes.
Okay, great. Now, yeah, let's do the theorem, change of basis. And this is in the same spirit that now if we want to change our basis, then what does the matrix of the transform? How does the matrix of the transform change? So recall the change of basis matrix is a matrix that we defined, which would lead us to change coordinatizations from basis B1 to B2. And this is useful in the change of basis theorem, because what we get is this. Yeah, that if the matrix of T with respect to these two bases are M1 and M2, then we have M2 is P inverse M1 P, where P is the change of basis matrix. And this is easy to prove using the above results. And this is left as an exercise. So this motivates the following. We say two matrices are similar. So let's do this portion first. Okay, yeah, similarity. This motivates the following, that we say two matrices A and B are similar, written like this, if there exists an invertible P, matrix P, which would be the change of basis matrix, such that B is P inverse AP. So you can check that this is indeed an equivalence relation. And the idea behind saying that these are similar is that if we have a vector, yeah, so let's say these are n cross n, then in Rn, the same linear transform T, the same linear transform T gives rise to the matrix B and A when we choose two different bases, B1 and B2. So these the idea is that these are similar because they correspond to the same linear transform with respect to some weird bases. We don't care about bases. So okay, so I guess let's move on to eigenvectors and eigenvalues, and if there is any question in change of basis which we would need, then I would recover that. So is that fine?
Yes.
Okay, great. Okay, so let's start with some definitions. So given a linear transform T from a vector space V to itself.
I'm sorry, could you please repeat the meaning of the definition again? Of A and B are similar. So A and B
Okay,
are similar.
sure. Wait.
So if we change the basis vectors of say Rn, and then A and B are similar if they with respect to if a linear transform A with respect to one base is equal to a linear transform A dash with respect to another base.
Mm, wait, could you repeat that?
So suppose we choose say two vectors as, so if we choose different bases, say two different bases, and so the linear transform will with respect to each will change, right? If we needed to give
Yeah, no, we have the same linear transform. This is fixed.
okay,
And
yeah,
what would change is the matrix of this linear transform with respect to these two
yeah,
bases.
yeah, the
So
matrix would change, yeah. The linear
yeah,
transform would remain.
the linear transform is same. So what similarity essentially means that we are saying that A
There,
is similar to B if we have a particular linear transform and two bases such that T with respect to B1 is A and T with respect to B2 is B.
yeah, got it.
Okay. So similar matrices have lot of same properties, like they have the same determinant and the same trace, and if one is invertible the other is invertible. So yeah, and okay, let's do this. So given linear transform T from V to V, a vector V is called an eigenvector of T if the first thing is V is non-zero and the second thing is that T applied to V scales V, as in T of V is lambda V for some scalar lambda, and lambda is called the eigenvalue of V. So, so in this picture, if we have a vector V, then if the linear transform is fixed, and we say this vector is an eigenvector because T scales this, as in let's say T of V is 2V, and then here 2 would be an eigenvalue. Okay, so is this definition clear?
Yes.
Okay, so we won't need this, but I put it here because this is a nice problem and it is hard, like if you don't know the idea. So it turns out that any linear transform can have at most n eigenvalues. Recall that we call lambda is an eigenvalue if it corresponds to an eigenvector. Like if there is a vector v such that PV is lambda v. Okay, so I have also given hints for some selected exercises at the end, and you can look at that. So yeah, we did similarity. Now let's motivate diagonalizability a bit. So the definition is this. So there are two equivalent definitions. First, let's talk about the matrix one. So a matrix A is said to be diagonalizable if there exists an invertible P so that P inverse T, AP is diagonal. And by diagonal, I mean, okay, yeah, by diagonal, I mean it has entries only on its diagonal, and the other entries are all 0. Yeah. So, in other words, using similarity, we say a matrix is diagonalizable if, let's say, A is similar to some diagonal matrix. Yeah. And equivalently, we can say that if there exists some basis consisting of eigenvectors. Now, why this is equivalent is because let's again consider R square. If we have two bases V1, if we have one basis V1, V2, and with respect to this basis, uh, and the basis vectors are eigenvectors, then that would mean that T sends V1 to, let's say, 3V1 and V2 to, let's say, 4V2. Then with respect to V1, V2, the matrix of T would be like 3, 0, 0, 4. And that is a diagonal matrix. And because of the change of basis theorem above, this is the same as saying that any matrix corresponding to T satisfies that there exists some P, which is like converting bases such that this is 3, 4, 0, 0. So for now, let's focus on this definition more.
Isn't matrix multiplication commutative?
No, matrix multiplication is not commutative.
Okay.
So as an example, you can take, let's see, 1, 0, and try this maybe. Okay, so you can look for counter examples, but it isn't commutative.
Yeah, okay.
Okay. So now the question is, why is diagonalization important? So the main idea is that similar matrices are essentially the same, and diagonal matrices are simple matrices. As in, to be more concrete, as in we can exponentiate a diagonal matrix very simply, as in if these, let's stick with 2 cross 2, if D is 2, 3, 0, 0, then D square is 4009, and D power n in general is 2 power n, 3 power n, 0, 0. But this is not so simple if we have a matrix, let's say 1, 1, 0, 1, and taking power, we can't, it is not easy to directly compute A power n. Okay, so this maybe motivates a little bit of why diagonal matrices are important. And we'll see another use of diagonalization in this lecture. Essentially, what we'll see is that diagonalizing will let us understand conics better, which would let us prove symmetries and all. Yeah.
Can you show once more like how diagonalization exactly works? I didn't get much.
Okay. Okay. Yeah. So, do you remember that definition of similarity of matrices? That A similar B if A if B is P inverse AP.
Yeah.
And so diagonalizability says that A is diagonalizable if A is similar to some diagonal matrix.
Oh, okay.
And don't worry about this definition right now. This
Okay.
won't be useful. Okay, so yeah. So the idea is that we can easily so that diagonal matrices are simple and we can easily tell, for example, whether they are invertible, whether we can easily exponentiate them. We can easily calculate their determinant by taking the product of that diagonal values. So yeah. Now, before coming to conics, we'll need one more thing. So that is orthogonal matrices and isometry. So let me try to motivate this. Wait. Okay. So the motivation for this would be, let's say, for isometry would be to rigorize congruency. Congruency. So in R square, when do you say that two shapes are congruent? And we would rigorize this using isometries. And let's do this first. So first, let's define some things. So if we have two vectors, x and y, in Rn, then we define their dot product as this: x1 y1 plus x2 y2 plus dot 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 x and yn, the product of the corresponding entries, and take the sum out. So this, and we'll use this for magnitude of a vector, which we define as this square is x dot x, which is the sum of squares of entries. So this would be the root of this, the positive root of this. And okay, we define a set of vectors v1, v2, dot 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 vn is called orthonormal if vi dot vj is 0 for I not equal to j and all vectors have magnitude 1, i.e. an orthonormal set means that the vectors are pairwise perpendicular and unit vectors. Something like this. So v1, v2 in this case would be called an orthonormal set of vectors. And it is a fact that orthonormal set of vectors, n vectors, is also linearly independent in Rn. So, and you can try to prove this. It is not too hard. Okay. Yeah. So now we define a matrix. Let's say a matrix A, which is an n by n matrix, to be orthogonal if A transpose A is the identity matrix. And notice that this definition has something to do with uh, the orthonormal vectors. That is that if we have an orthogonal matrix, and let's write it as a11 an1 1n, this thing, then A transpose A would be 1 2. N1, wait, this thing, times A and the ijth entry of this would be multiplying the ith row of this with the jth column, and that would be this. The ith row of this would be a I1, no, a1i, a2i, a-n-i multiplied by this. The jth row of this would be a jth column would be a1j, a-n-j, and notice that this is just the dot product of the column of the ith column with the jth column of a. This is a1i, a2i, a-n-i dotted with a1j, a2j, a-n-j. So that means that A transpose A for any matrix is this. If A is A has columns v1, vn, then A transpose A would be v1 dot v1, v1 dot v2 dot dot dot, v1 dot vn, v2 dot v2, and so on. So a matrix being orthogonal is equivalent to its columns being orthonormal, because v1 dot v1 is 1, vi dot vi is the diagonal entry. If this is I, then this is 1, and vi dot vj would be 0. So this is the result that we'll use, that a matrix P is orthogonal if and only if its columns are orthonormal. Okay, so finally, let's introduce isometries, which is as follows. Yeah, a map tau from Rn to Rn is said to be an isometry if it is distance preserving, which means that notice that the distance of two vectors in Rn is this length, which would be y minus x magnitude. So isometry would mean that if distance, this is the distance between t of x and tau of y, which is equal to the distance between x and y. So do you see why this sort of recognizes congruency? As in, we say two shapes S and T are congruent. Let's say they are subsets of the same space Rn. If there exists an isometry which maps S, the set, to T. Okay. So again, this is not too hard, that you can prove that isometries preserve angles, and you do this essentially using that take any triangle ABC and take its image tau A, tau B, tau C. Then since these all lengths are same by definition of isometries, the angle would also be the same, and you are done. So, and now let's prove this.
Will that be true for higher dimensions?
What?
That thing will also be true for higher dimensions. How is the angle different?
Oh, okay. So for higher dimensions, we define angle as angle between, let's say, two vectors x and y to be cos inverse of x dot y over norm x norm y, and this always belongs to 0 to pi. And for, let's say, for R3 we don't define angles like 270 or something. We don't define that. We only have angles like this. But for now, let's stick to R square, and there we can define angles in the normal Euclidean way like this. Yeah. So if you are uncomfortable with like the abstract definition of angle, you can
No, it's
like just consider the dot product and forget about angles. We won't need angles. So okay, yeah, sure. So okay, we'll need this exercise, so let's do this nicely. So okay, so this is that prove that this map from Rn to Rn given by the vector v gets sent to, this would be a column vector because something like this xn, we get sent to pv plus some scaling vector b, which is also belongs to Rn, prove that this is an isometry if and only if p is orthogonal. So we do this as follows. So let's compute this thing. Let's call this map T, tau, and this thing is this u plus p minus pv plus b norm squared, which is just bb cancels, p u minus v squared, which is pu minus v dotted with itself, which is, notice that for column vectors x dot y is x transpose y and also y transpose x. So this would be pu minus v transpose pu minus v, which would be u minus v transpose. This would be just the row vector, like transposing a column vectors, we get a row vector, and then we would have p transpose p, then u minus v again. And for this to be equal to, and we need this to be equal to, let's take a question mark here, we need this to be equal to norm of u minus v squared, which is u minus v dot u minus v, i.e. this thing. So if p is orthogonal, that means p transpose p is identity, then this is true. Conversely, if this equality is true, then just take like u minus v is an arbitrary vector, and just take this to be this vector 1 0 in the ith place for arbitrary value of I, then we get 0 0 1 0 p transpose p 0 0 1 0 is yeah, this was 1 0 and this. And this is exactly the ith entry of P transpose P. So we get the ith entry of P transpose. This whole thing is that, and this is just 1 for I. So the ith entry of P transpose P would be ith entry would be 1, and for the ijth entry, notice that if we, instead of this, because an isometry also preserves angles, it also preserves dot product. So considering let's say, yeah, t of some vector x dot t of y, we would have this is x dot y, and from that we would have that px plus let's say this, yeah, t of x minus, let's fix a 0, and this dotted with any other thing, 0 would be equal to x dot y, and using this, and that t is given by this, we get that using the exact same expansion as here, we get that for any vectors, x transpose py would be x transpose y, and then take x to be the column vector with 1 at the ith place, and y to be the vector with 1 at the jth place, then this thing would be 0 if I is not equal to j, and LHS left hand side would be the ijth entry of P transpose P. So that would guarantee that P transpose P is identity, which means that we just proved that a map of this form is an isometry if and only if P is orthogonal. So actually a general result is true that in fact all isometries are of this type, but the proof of this is slightly non-trivial and we won't need this in this lecture. So for now, keep in mind this exercise, which we would need later, that all isometries are given by these type of maps. Okay. So now let's take spectral theorem. And this says that every real symmetric matrix A is diagonalizable with an orthogonal change of bases. And what I mean by this is that a real symmetric matrix A, symmetric matrix means A is A transpose, and A is similar to D, as in every real symmetric matrix is diagonalizable. And moreover, we have an orthogonal matrix which diagonalizes A, as in we have an orthogonal matrix such that A is PD P inverse. Okay, now we'll be basically using this theorem to answer our question about conics. So is the statement of the theorem clear?
Yes.
Okay, great. So finally, let's come to conics. So first we'll just define some definitions for convenience. So a quadratic form in n variables is just a homogeneous degree 2 polynomial. For example, this here, like it needs to be homogeneous, as in each terms must have degree 2, and Yeah, homogeneous and degree 2 polynomial. So this is a quadratic form in 3 variables because we have x, y, and z. And something like x squared plus y squared would be a quadratic form in 2 variables. Okay. So we can actually write this in a matrix notation as something like this. So this is the quadratic form, like the polynomial, and we can write this as x1 dot dot xn a x1 dot dot xn, just because let's say you have, let's take the same example, x square plus y square plus 3z square plus 2xy, and we can write this as x, y, z, and on the diagonals, so the coefficient 1 would come here because this term selects the first column in here and the first row in here. So this coefficient comes here, this coefficient come here, and now the yz coefficients are these two, which are, let's say, 0, and then xz are 0, and for xy we split this equally, as in xy plus xy. You will see why, essentially so that this becomes a symmetric matrix and so that we can diagonalize it. So let's just check this by expanding for some clarity. And this is like x, y, z, x plus y, x plus y, and then 3z, which would be x square plus xy plus yx plus y square plus 3z square, which is the same thing. So in general, if you have, say, something like this, plus c xy plus dx plus ey plus, wait, no, sorry, something like this. This is a quadratic form in 2 variables. Then you can write this as follows: a, b, c by 2, c by 2, and then xy. So now we define a conic, as we defined previously, to be the set of roots of a polynomial of degree 2 in x and y. For example, this is a circle, this is another conic, and in general, roots of this type of equation. And now a remark here that we, as of now, don't restrict things to be non-degenerate. For example, we would also include x plus y 0 to be a conic, although it is just a line. And we would also include x squared plus y squared plus 1 is 0 to be a conic, even though it's empty. And we would call these not conics to be degenerate conics. So we would call that whenever this locus is 2 lines or a single line, a point, or empty, we call it degenerate, and otherwise we call it non-degenerate. And as we'll see, we can classify non-degenerate conics in a nice way. So now these are the questions that I mentioned, that why does the root of a quadratic equation not look like this but have this weird symmetry, which is point symmetry as well as 2 line symmetries. And in general, yeah, that why do intersections of cones with planes, this set of curves is exactly the same set as solving a 2-degree equation. And we would try to answer this using by basically trying to understand conics by classifying them. So this is the main theorem that we would do, is that every non-degenerate conic is congruent, and by congruent we mean the isometries thing, congruent to one of the following shapes: an ellipse, which this is the standard form, a hyperbola, or a parabola. And now the main thing in this proof is the following, that if we have this as our conic, then look at only the degree 2 portion, and we write this as this. And now notice that if instead this degree 2 portion was very simple, as in something like x squared plus 2y squared, and then we would have, let's say, something plus x plus let's say minus 3, then we could
Shouldn't
easily...
it be A, C by 2, C by 2, and B?
Oh yeah, thanks. Yeah, it should be that only. A, C by 2, C by 2, and B. And okay, so the main idea is that if, let's say, for now that C was 0 and the conic was something like this, then what we could do is complete the square in this portion to get x plus half squared minus 1 by 4 plus 2y squared minus 3. And then this would be essentially congruent to the conic x squared plus 2y squared is 3 plus 1 by 4, which would be an ellipse. And the symmetry properties for these would be obvious, because if xy belongs, then minus xy plus minus x plus minus y belongs for any choice of plus minuses. So the idea is that if we can convert this quadratic portion into something which doesn't have an xy term, then the problem would be easy. So that we do using diagonalization of this real symmetric matrix, which we know exists using spectral theorem. So let's get into the proof. So this is the degree 2 portion. And yeah, this is C, not A. And this can be written as this. And we diagonalize this by an orthonormal change of basis. You will see why we need this to be orthogonal in a minute. So recall that a diagonalization was, okay, let's convert this into a C. Okay, so the diagonalization was, this is PDP inverse, where P is an orthogonal matrix. And because it is orthogonal, that means that P inverse is P transpose. Because notice orthogonal meant P transpose P is identity, which means that P transpose is P inverse. So by spectral theorem, we have this, that this is PDP transpose, where P is orthogonal. And now let xy denote coordinates for R square with respect to this orthonormal basis, by which I mean that consider the columns of this change of basis matrix, and let these columns be v1, v2. In this case, because P is only 2 cross 2, so there will be two things. And because of the exercise that the columns of an orthogonal matrix are orthonormal, we have that v1 and v2 look like this. They are perpendicular and unit vectors. And what we do is look at the same equation where initially we took coordinates x and y, which you can visualize as coordinate with respect to the standard basis, and we convert them to capital X, capital Y, which are coordinates with respect to this basis. And recall that because of the change of basis theorem, we have that the conversion is given by this. And this lets us simplify this very nicely using, we know this is this thing here, and then we write small x small this column vector as this, so that this is the transpose of this, and this is the same matrix, and the transpose would be like AB transpose is B transpose A transpose. So this becomes XYP transpose, and then we diagonalize this matrix, then PXY, and because P is orthogonal, P transpose P is identity. So these two and these two terms are identity. So we are left with this. And this is exactly what we wanted. And now we also convert this into this as a linear combination in terms of capital X, capital Y by the same thing using change of basis, as this is the degree 1 term of the conic, and this is dE times xy, which is dE times P change of basis matrix times capital X, capital Y, which is some GH vector times XY vector. And now if D is the diagonal matrix lambda 1, lambda 2, then we split into cases. So we already got that in terms of this nice orthonormal, the v1, v2 coordinates, the roots in terms of capital X, capital Y correspond to the quadratic equation, which is a bit simpler, something like lambda 1, something like xy lambda 1, lambda 2, 0, 0, xy for the degree 2 portion, plus some gx, plus some hy, plus the constant f, which is 0. And this becomes lambda 1 x squared plus lambda 2 y squared plus gx plus hy plus f is 0. And for now, let's consider the case lambda 1 is greater than 0 and lambda 2 is greater than 0. And other cases are similar. In this case, we can complete the square to get some x tilde y tilde. Let me illustrate. So suppose, let's say we have 2 capital X square plus 3y square plus 4x minus some 10 is 0. And so we can complete the square as in 2 times x plus 1 whole square and minus whatever constant we want, minus 2, which is this x, this plus this term, plus 2y square minus 10. And then if we let x tilde to be x plus 1 and y tilde to be y, then we get the equation something like plus 2y square 3y tilde squared is some constant 12, and we know that this is an ellipse. So we do the same thing in general here, that since lambda 1 and lambda 2 are non-zero, we can complete the square to get some x tilde y tilde to be some x y plus some constant vector b. Here by b I mean some alpha beta, where alpha beta are real numbers, so that our equation becomes this. And now notice that since lambda 1 lambda 2 were both positive, if p is less equal 0, then this is degenerate, because if p is less than 0, then we get a contradiction, because sum of squares is always positive. And if p is 0, then the only solution is x tilde is y tilde is 0, which also we don't want. So in the case of p is greater than 0, we clearly see that this is an equation of an ellipse by dividing by p. So something like lambda 1 over p x tilde square plus lambda 2 over p y tilde square is 1. And then we get x tilde over under root p by under root lambda 1 squared plus y tilde over root p by lambda 2 whole squared is 1. And this is an ellipse. Now, there is one thing left, that whatever we did in during the change of bases, why doesn't it affect the congruency of the shape? And this is not trivial, as in, suppose I did something like a circle initially and chose some random coordinates like this, and I calculated the equation in these coordinates, then in fact that wouldn't be a circle anymore. But because because apart from translation, the only thing we did was pick these coordinates, which are orthonormal, as in unit vectors which are perpendicular, we would get that this is indeed congruent. More precisely, consider consider the map sending small x small y to capital X tilde capital Y tilde, and notice that capital X tilde capital Y tilde was this capital XY plus b vector, and then capital X capital Y vector was because of the change of basis this thing. So we get that small x small y, this vector goes to p inverse xy plus b, and this is an isometry, as p is orthogonal if and only if p inverse is orthogonal. You can check this, and this is exactly what we did in a previous exercise. And moreover, notice that where does this map send our conic, which is okay. So this map, where from xy to x tilde y tilde capital, where does this send our original 2-degree equation? So originally we had r square and some shape, which was the set of this shape was the set of small x small y, such that some equation is satisfied. This thing, yeah, plus dA plus ey plus f is 0, and with this isometry, we proved that this is an isometry. This shape gets sent to x tilde y tilde. And we just showed that in terms of x tilde y tilde, this equation here is given by uh, an ellipse like x tilde square lambda 1 plus lambda 2 y tilde square is some constant p. So all these xy satisfying this, which are the roots of this equation, get sent to x tilde y tilde, which are the roots of this transformed equation. So all these get sent to an ellipse, and we know all the nice symmetrical properties of this. So, and further, because this is an isometry, this map, hence all the distances are preserved and all the angles are preserved, and so these two shapes are congruent. So this must also have the same symmetry. Okay. And the cases of, so the cases lambda 1 less than 0 and lambda 2 less than 0 are, this case again gives an ellipse, and you just multiply the whole equation by -1 and do the same procedure. The cases of lambda 1, lambda 2, lambda 1 was the entries of the diagonal thing, like the main quadratic portion. So if these have opposite sign, then we get a hyperbola. You can check this as an exercise. And if one of lambda 1, lambda 2 is 0, then we get a parabola. Notice that if both are 0, then we have a degenerate conic, because then this equation, this whole thing would be 0, which means the quadratic portion would be 0. So that would be a line. So now, after classifying like the solutions to degree 2 equation as that, we can prove the, let me add a page here. We can prove the symmetry properties by just saying that such a conic is congruent to the either an ellipse, a hyperbola, or a parabola defined in this theorem. Where is it? Defined here. And then these shapes clearly have the nice symmetry. Parabola doesn't have a point symmetry, but it has a line symmetry. So any non-degenerate conic has a line symmetry, and let's say bounded conics have point symmetry, as well as hyperbolas have point symmetry. So this is all I've planned to cover today. So do you have any questions? Yeah. Hello, am I audible?
Yeah, no questions.
Okay. So, okay, yeah.
Oh, also,
You
approximately
can,
how long will it take more?
5 to 10 minutes, I guess.
Oh, can you repeat? My net disconnected. Sorry.
5 to 10 minutes.
Sure. No worries.
Okay. So, using the exact same procedure, we can deduce symmetries about other things. So, we can, so, okay, try this problem.
Isn't this just by like for 2 degree stuff and you just do same thing, no?
Yeah, this is the exact same thing in three, like in three variables, and so the roots of this look like a cone, which may not be right circular, but it would have an axis because of the exact same thing as we diagonalized this A. Using the exact same procedure, we would prove that such equations, the roots of such would have an axis, and about which it would be symmetric, and things like it would have, like the base would be an ellipse and this sort of things. Yeah, so using this we can also prove that, for example, if we also include 2 degree and 1 degree, yeah, if we also include 1 degree terms in this to be something like this plus some 1 degree thing, x plus y is some 4 or something, then we can also use the same procedure to derive symmetries of this, that this would look something like an ellipsoid or something else, but would always have, let's say, an axial symmetry, an axis, and also point symmetry and all that. Okay, so these are some problems for you guys to try, and I have also given some hints for these, and I'll be sharing. These are hints for exercises, and here are hints for problems, and I'll be sharing this PDF also. So, any final questions?
Can we do something more with this?
Something more. Okay. Using spectral theorem, you mean?
Yeah. Yes.
Yeah. So we can do like, okay. So try this. Like, wait. So let's say you have a function in xy from r square to r, something like sine x plus cos xy, something like this. And suppose you want to find, let's say, a local minima of this function, or let's say a global minima for this function. So the way to do that would be uh, to find something called like the critical point, which would mean that we would need that in one direction the derivative which we write as this of the function is 0, and in the other direction also 0. But suppose you want to, but there can be many such cases that this can be a sort of global maxima instead of a minima, and this could be something like a saddle. So suppose you want to find out whether it's a saddle point or a minima or a maxima, then that also uses the same sort of ideas. So uh, briefly, like there is, for any, let's say, smooth function, there is a Taylor's theorem for two variables, which says something like that this is around some point x star y star, that this is roughly equal to like this plus, let's say, a 1 degree term, which would include this, and plus the 2 degree term would look a lot like what we did, and this is like called the Hessian, and it's a matrix, and we would have this. So in that sort of optimization also, we need to figure out whether this quadratic form is always positive or always negative, to check whether we have a local maxima or minima. And in that case also, spectral theorem comes in handy. So we can diagonalize this, and then you can check that this is always positive if and only if the diagonal matrix has positive entries, and always negative if the diagonal matrix has negative entries. And in general, whenever we have in general, whenever we have some quadratic form, let's say in 2 variables, A is a symmetric matrix, then if we want to try to understand this quadratic form, as in deduce properties about it, then spectral theorem comes in handy, and we have like this up to a change of basis. This is exactly the normal thing, like x tilde lambda 1 squared plus lambda 2x y tilde squared. And yeah, so in general, if you have in any case a symmetric matrix, then if you want to understand that matrix, as in deduce properties about that particular matrix, or more importantly this thing which comes up a lot, the quadratic form, then because spectral theorem tells us that this matrix is diagonalizable, you get that this particular matrix is very simple, as in is use any, you can easily exponentiate it or determine properties about it. And similarly, this particular homogeneous polynomial, which is like a general homogeneous polynomial, can be converted into this, and you can deduce all sorts of properties using diagonalization. Okay, so yeah, in general, spectral theorem is very useful in a lot of situations. Did that answer your question?
Yeah.
Okay, any other questions? Okay.
Okay, I'll stop recording.
Okay, sure.